Okay, so the general framework of the talk is about graph compression. Okay, we have a graph and we want to represent it in a succinct manner. And we want to preserve certain properties of the graph, whether exactly or approximately. And this talk will revolve around distances. So two types, or two variations of the problem of compressing graphs is edge specification, in which our goal is a small enough number of edges in the resulting graph, and vertex specification, where we keep only important or mostly important nodes, which we refer to as terminals. Okay, so we care about, in this talk, we care about terminal distances. We have a graph. We think of it as a huge network. And we have k terminals, T1 to Tk, which is a subset of the vertices. And we care about terminal distances. The graph, the edges of the graph are weighted. And the weights induce the shortest path distance metric on the graph, which will be denoted like this. Okay? So what is our goal? Our goal is to find a graph, ignore for a minute the word minor, a graph G prime, which is spanned only on the terminals. We can create new edges, and we reweight the edges. Okay, so new edges and new weights. And we want the distances, the new distances, we want them to satisfy these two inequalities. This inequality will say that the new metric, okay, notice that this is the metric in G prime with respect to W prime. And this inequality will refer to it as the new metric dominates the old metric. And the second inequality it means how large is the new metric. There shouldn't be a prime here. It should be G. With respect to the previous metric. And alpha is called the distortion. Okay, so far? Okay, so let's do an example. So if this is G, okay, I should get back to the minor thing. So we want G prime to be a minor of the original graph. Okay? Which means it is constructed from the original graph by contraction of edges.
So why not take the original graph? I mean, some other?
So we want the new graph to be spanned only on the terminals. This is the removing Steiner points part of the title. Okay, so we have terminals which are colored yellow throughout the top. And we have these Steiner nodes which we want to get rid of. Okay? Contraction of edges means that we identify the new nodes as sets of old nodes, which are connected components, and we simply contract them to a single node. Mm-hmm. Okay?
And is it obvious that there always exists such a node?
No. I don't think so, no. Not with non-trivial. Okay, so we can always take some connected components and contract them. There is always a minor which is spanned only on the terminals. But we want to bound somehow the distortion in the distance. Okay, and we want this bound, I will say, we want it to depend only on k, if not a constant. The constant is k is the number of terminals, and not by the size of the graph.
So it's not so obvious that you can do this with alpha depending
on k only? No, it's not trivial.
K is an input?
The set of terminals is a part of the input, and k is simply the number of terminals. Okay? So what happens if we contract this set to a new node and this set? We get this graph. We can reweight the edges. So we weighted this edge 8 and this edge also 8. And why do we do this? Why do we have to? We can't do less than 8. Because the original distance from A to B is 8 in the original graph. Okay, and we want the part of domination here. So we can't do less than 8. Okay, we have no reason to put more. And 8 again here. So the distance between A and C in the original graph is 10, and here it's 16, so the distortion is up by 1.6. Okay, are we clear so far?
Just to understand, I got the problem. So you're
Okay.
given a subset of the vertices.
I'm given a graph with edge weights and a subset of the vertices.
And you want to find the minor such that each of these vertices will belong to a different set in the minor,
Yes.
and etc. So on and so forth.
Yeah.
That's this constraint.
Yeah. To be really formally exact, I don't really demand that each terminal will belong to, as the formal definition of the problem, I don't demand that each terminal belongs to a different set. I can create any minor that results in K and embed the terminals inside. Okay.
Maybe you said this, but where do the numbers 8 and 8 come from?
Yeah, the distance between A and B in the original graph is 8.
I see.
So in order for the new metric to dominate,
See, it's not 8.
it's 8, 3, 2, and 3.
Oh, okay, I can see that.
Yeah, this seems shorter, but the weights are, it's tricky. Took me a while also. Okay, and since we want the new metric to dominate the old metric, we can assign less weight. So actually, W prime is really induced by the original graph. It's not, we can't jiggle with it any. Okay, so why do we require a minor? We want to maintain certain structures in the graph. Okay, for example, planarity, or the original problem was stated over trees, and we want a tree to give a trees. Okay, so we want to maintain certain structural properties, and also if we don't require a minor, then the problem is trivial. We simply output the complete graph over terminals with edges, the weights simply the original distances, and we are done.
I mean, maybe you could say you want an above edge to be at most.
So yeah, we can restrict. There are other restrictions other than minors. Perhaps I will talk about it in the end of the talk. There are other restrictions. Yeah.
Isn't that G prime should be always a kind of spanning tree of the original graph? Of the terminals?
No, it doesn't have to be a spanning tree, I think.
No, I mean,
It's
G prime
not-
should be always a tree?
No,
No?
no. Just take, for example, a cycle with the terminals. On the cycle, take the graph only on the terminals. Take a cycle. You can't transform it to a tree and keep the distances. Okay? Okay, so our main result is that every K terminal G admits a minor G prime, which has distortion polylogarithmic in the number of terminals. Okay?
So it is true that you can do something which depends only on K.
It wasn't true before we proved it.
Now it's true.
Now it's true. Now it's trivial. Okay?
Okay.
So K here is the number of terminals. It's not
Yeah.
the size of the graph.
No. That's the main issue, to construct a minor in which the distortion is not dependent in the size of the original graph, only in the number of terminals, hopefully constant, but we are not there yet. Okay?
I see. So okay. So I think my confusion is over. So there are sort of similar results about the cut structure.
Yeah.
Okay.
Yeah.
And this is about
The distances, yes.
The distances. And you know any lower bound?
Yeah, there is one lower bound, which is 8. I will talk about it in a minute.
I see. So you don't know even log K?
No. We don't have any lower bounds other than 8.
Do you believe it could be constant?
I believe it's hard to say. I believe that no, but I cannot really say. Okay, so there was no, as to your question before, that it's known to do with distortion depending on K. Previously, there was no other upper bound. A simple argument, which I will show in a minute, achieves a distortion of linear in K. So this is a major improvement from linear to polylogarithmic. So a small history lesson. So the problem originated in a paper by Gupta, which showed that every tree has a tree G prime with distortion only on the terminals, which achieves this distortion of 8. A later paper by Chan, Xia, Konjevod, and Richa. Richa? Isha? Okay. So they showed that 8 is actually optimal. And they showed that the algorithm, the original algorithm of Gupta, actually achieves not just another tree, but a minor. Okay? And they actually defined the problem for general graphs, the problem that I stated earlier. Okay, so Basu and Gupta continued a little bit in the pursuit of special kinds of graphs and showed constant distortion for orthoplanar graphs. In a paper by Englert, Gupta, Karl Gammer, Reke, Talgam Cohen, and Talwar from 2010, so they constructed a randomized minor of a graph. A randomized minor is simply a convex combination of minors of G. And this randomized minor achieves expected stretch logarithmic in the number of terminals. This is K, I remind you. And for planar graphs, it was a constant. They showed that this has application to sparsifiers preserving flow and cuts, as you said before. When we deal with randomized minors, there is some duality between distances and cuts and flows. Okay, so this is about randomized minors. Our result, as I said, showed a single minor that preserves all distances approximately.
So even in this randomized case, there is no constant upper bound, right? But there's only constant lower
bound of 8, yes. So terminal-centered minors, this is actually the type of minors we deal with. We take a partial partition of the original vertex set, and for every such subset, the respective terminal is in the subset, and the induced graph is connected. Okay, as you see here. And this constructs a minor by contracting each of these clusters to a supernode. And then there is a natural embedding of T inside this new minor. We simply exchange Vj by Tj, assign weights, and this claim is almost trivial, that the new metric dominates the original metric. Okay, because of the way we assign the weights. Okay, so what is the most naive approach? What is the simplest thing we can do? Can you think of? How do we construct such a minor in a very simple way?
Balls, like balls.
Okay, so balls, they don't necessarily, we need to partition the vertices. Okay, so in the original definition, I said a partial partition, but for our problem, we need a real partition. We can't leave any Steiner nodes behind.
Well, you can attach every Steiner node to the closest terminal.
Exactly. Okay, so we simply attach every Steiner node to its closest terminal. There's a small subtlety here. I will explain it in a minute. Okay, so V1 is simply all the Steiner nodes, including all the nodes, actually, which are closer to T1 than anyone else, and V2 as well. But there is a small subtlety of resolving ties. Okay, we can't resolve ties arbitrarily. Because, for example, these two nodes are in the same distance from T2 and T3. But if we contract this node to T3, we cannot contract this node to T2. Because then it will be no longer be a minor. Okay? Yeah. No, but the thing is that we break the connectivity. Okay, so it's no longer connected. We need it to be connected. And the ties are broken by the ordering of T. If we do it in order, okay, so it seemed really trivial to do it in order, but it's crucial. Okay.
You can perturbate each point and then you don't have any ties.
I think there's a small chance that you'll perturbate you'll hurt the connectivity, I think. Maybe it works, I don't know, I haven't thought of that. The ordering seemed, it did the work, so I didn't keep thinking about it. Okay, so now we get terminal-centered minor only on the terminals. And again, it's almost, now that I've mentioned the tie-breaking thing, it's almost trivial that the algorithm induces a minor. And I claim that each path in the original graph induces a path. There's a natural path that it induces here. Whenever our path goes from one cluster to another, there will be an edge here between the respective terminals. So for example, if we take a path from T1 to T3, this edge remained in the same cluster of T1, so for all our concern, we stayed here. Now we move to the next cluster, and now we move again. Okay? So this induced path in G prime, if we eliminate cycles, because it could be the case that we go in and out of a cluster. So if we eliminate cycles, we get a path here which has no more than k-1 edges, because it's a simple path. So it remains to bound the length of a single edge of such a path. Okay? So when does a path cross between clusters? When there was an edge here, in which one endpoint was contracted here and the other was contracted there. Right? This creates an edge in the new path which crosses clusters. So, yeah?
In the case of the ties in the former slide, why can you duplicate? Whenever you get a tie, you just duplicate the vertex and associate one to one cluster and the other one to put some zero.
And connect them by an edge?
Weight or epsilon weight.
I'm not sure it results in a minor of the original graph. I don't know. Again, I haven't given it much thought since this is not the main issue. I haven't given it much thought, but I don't know. It could work. Okay, so what can we say about these distances? The distance between U and T1 is at most the distance between U and S, right? Because otherwise U would be contracted here. And again here. Okay? So what we get is that the weight of this edge is not more than the distance between T1 and T2. It is exactly the distance between T1 and T2, by the way we define W prime. And this is not more than this plus this plus this, the sum of these distances, which is at most the length of this path. So therefore, we got an upper bound of k-1. Okay? So this idea holds some of the ideas in our result, but we need to allow more flexibility in order to get a better upper bound. So what we do is we grow these connected components gradually. We don't do it at once. Okay, so we start with Vj being only the respective terminal, and then we start growing them gradually. Okay? So in every iteration of the algorithm, we pick a random radius and create a connected cluster around the terminal. Okay? Okay? So two major differences with respect to prior results is that we don't extend to clusters from which we can for which we cannot get in the present state of the graph. Okay, so even though this radius will, in the next iteration, it will become 4. Okay, it's not really random, so I know it's going to be 4. This cluster will not grow here. Okay, because we want the clusters to be connected. And another thing is that the expected radius, we insist that it grows, it increases, it strictly increases in each iteration.
So your algorithm is randomized?
Yeah.
So what's the difference between the other
that ours achieves a minor with high probability and not an expected distortion. The distortion is achieved with high probability over all pairs of terminals. Okay, so as I said, this became 4, but it didn't go here. And we stopped the algorithm when we covered the entire graph. Okay, so the idea is clear? Okay, so how do we analyze this? So we fixed 2 terminals, S and T. This is the difference that answers your question. What?
Can you go back?
Yeah.
So what happens if I pick a too large radius and then bolts intersect?
So you simply, okay, so what the algorithm actually does is that when this terminal picks a radius, it deletes the other clusters from the graph. It leaves only the cluster of the respective terminal and the uncovered Steiner points. And it has to advance in this graph, in the distances in this graph. So if some node, so if some part becomes disconnected, we can't reach it. Okay? So this is exactly what the algorithm does. I was trying to avoid it, but.
So there is some ordering. I mean.
Again, there is some ordering, but yeah, of course. And we also depend on what happened in the previous iterations. So for analysis, we fix 2 terminals, and we fix some shortest path between them in G. And we show that with high probability, the final minor G prime has a path of length polylogarithmic times the original distance. Okay? And by an upper bound, we show that there exists, with high probability, there exists a minor in which all the distances are preserved approximately with this distortion. Okay, this is the major difference between this and prior results. Okay, which I say here. Okay, so for sake of analysis, we fix P star, as I said, and we maintain, throughout the analysis, we maintain a path P, which I'll explain how we update it. But this P is maintained only for sake of analysis. It's not an actual part of the algorithm. So there are 5 terminals in this example, and we start executing the algorithm. So T1 conquers some part of the path, T2. Now we get to T3. So the radius of T3 allowed it to reach the path in this manner. So what we do, we update P to have a detour here. Okay, so this is the new P. These are called detours, which are actually paths in the original graph. Okay, we know that the length of this path is upper bounded by the radius I just picked. Okay, and we need to control the length of these detours. Why is that? Just a small reminder. Okay, so for now assume G has unit weight. So here there's a detour of length 10, and there's a detour of length 10. What happens when I contract the clusters? The detours in G become edges in G prime. Okay, so if I bounded the length of the detour, I bound the new distance. Okay, so the distance, the length of P, of the updated path that I keep, is always an upper bound on the distance between terminals in the minor that I construct. So this is why I want to keep it small. Okay, so I continue the execution of the algorithm. Now, when I have such a cluster, I have no reason to keep this detour. So I delete everything and simply detour everything. Yeah?
Can you just go back a little bit?
Yeah.
You had the G prime. This is the opposite notation of what you had before? Or am I not following?
No, what I said, okay, so this is G. And P is a path in G now. What happens when I contract the clusters? Okay, so what will happen is this will become an edge between this node and this node in G prime. And what will be the weight of this edge? According to W prime, the weight will be 11, which is 10 plus this. Okay, again, everything is an upper bound. It's not an exact estimate. Okay, does this answer your question?
The original graph is unweighted?
No, only in this example. It's all the same if the graph is weighted, just for simplicity of examples. Okay, so again, this is crucial in the analysis. I will not get into the most technical part, but the fact that we resign and send certain detours is crucial, as well as the fact that if now T3 conquered another part of the path, we don't need to really to get here and then go back. We can simply join the detours, and this bounds the number of detours in every stage by k. Okay, this is important. So there is some correlation between the number of clusters that intersect P in a single iteration and the number of detours. Okay? And then, so I need to bound the number of clusters intersecting P. And this is a second result in our paper. Okay, so a stochastic decomposition of a metric space is simply a distribution over partitions of the space. And the theorem from 96 by Bartal states that every endpoint metric space, given parameter delta, which stands for diameter, there is a distribution such that for every partition in the support of the distribution, every cluster has diameter at most delta, and there is a separation probability. Every two points in the metric space, the probability that they are separated, meaning that there is a cluster such that X is in the cluster and Y is not, is upper bounded by some, it's not a constant, times the ratio of their distance and the diameter, the parameter. Okay? So it's proportional to this ratio. Okay, so we need a stronger property of these decompositions. So again, let's take some path in the, some shortest path in the metric space, which is, we consider a metric space as the complete graph for this context, okay? And let's assume this is the partition. So we defined the degree of separation, okay, of the path with respect to the partition to be the number of clusters which meet the path. Meet means intersect. Okay, so the definition of ZP is clear?
In the previous examples when you showed like these two clusters, that one is...
So when we bound after we divide the iterations into the first iteration and there are two kinds of iterations. At one of them I ignore such double detours, and in one of them it doesn't matter. So again, the technical analysis, I won't get into it, but at some point it's important. Okay, so you have to read the paper if you want the juicy details. Okay, or talk to me afterwards. Okay, so in addition to the previous two properties of the stochastic partition, we need another property, which we call the degree of separation. Again, we want the probability, okay, for every P which is short enough, the probability of ZP to be large is exponentially decreasing in T. Okay? Are you with me? Nod your head. Okay. So the separation probability alone only gives us a weaker bound. Okay? Because if you take the expected size of ZP by the separation probability, it's a constant. Okay, and then you get that the probability that ZP is larger than T is at most 1 over T by Markov inequality. Okay, so this is weaker. Using just the separation probability is weaker than what we showed. Okay, so how do we prove that such a partition exists? Actually, we use more or less the same partition that Bartal used. For every point in the metric space, we sample a random radius. This is the truncated exponential distribution with parameter delta over log n. N is the number of points in the space. R is bounded, and it's almost memoryless. Okay? Okay, so, and again, just see, sorry, that we grow a ball, but we only take new points that were not earlier covered. Okay, and another thing, a center can be outside of its cluster. This is the center of the blue, this is blue, right? Okay, so this is the center of the blue ball. It can be outside of its cluster. Okay? And then we continue until we cover the entire space. Now, again, this is the same partition that, the same distribution that Bartal used, so we don't prove the first two properties, but the third property, I will show the flavor of the proof. So we fix some shortest path and some t, positive t. We divide the points, as I said, there are two properties of the distribution, of the truncated distribution that we want to use. The first is that it's bounded, and the second is that it's almost memoryless. So we divide the points in the metric space into points which are far from the path and points that are close to the path. So for points that are far to the path, since this distribution is bounded, the probability that we will even touch the path is small. Okay? It's small, 1 over n. Okay, so by the Chernoff bound, the probability that the number of poles is at least t over 2 is exponentially small in t. Okay? Now, for close points, for near points, if x touches the path, with constant probability, it will cover the entire path. Okay? Because it's close to the path, and the distribution is almost memoryless. So again, since the balls are independent, the radius of each ball is independent in the radii of the other points, of the other balls, then again, the probability, the number of balls that meet P is larger than T over 2. This probability is exponentially small in T. Okay? So this is more or less the proof. Again, I didn't go into the details. Okay, and from here I will skip directly to the result, again, without messing my hands with the technical details. With high probability, this is what we wanted. The length of this maintained path in the end of the execution is at most polylogarithmic times the distance, the original distance. Okay?
Can you maybe say a few words about the relation?
Again.
Say something about covering paths?
I said it. Okay, sorry.
I mean, how does it relate to?
Okay, so.
You have more time.
I have more time? I was sure I was way behind.
No, you have about 8 more minutes.
Wow. I can do miracles in 8 more minutes. Okay, so.
You can say a lot. You can speak slowly.
Okay, sure. So, so the algorithm samples a radius for each terminal, which is distributed exponentially with, so there was, I won't go back, there was this B, which was something like this. And in iteration I, we sample radius with the expected value of B to the I. Okay? So up to some point, since we insisted that no more than k detours at a time, up to some point, this expected radius is no more than the length of the entire path divided by k squared even. So these k detours don't interrupt. They don't add much relatively to the original distance. I measure distortion relatively to the original distance. Okay? Now, from this point on, we want as few detours as possible. Right? So again, since we grow, the detours are constructed by growing balls around each terminal. We want as few balls to intersect the path P, or the unassigned parts of P, as possible. Okay? Ofer?
Yeah.
You asked. So no, I'm answering your question. Okay? So this is the relation between the number of balls intersecting a path and the number of detours. What?
It seems like you need a strong diameter.
Yeah, so I need a strong diameter, so I cheated a little bit. Okay, because when we deal, the result that I show here is a simplified version of our result from the paper. Because, okay, so if you work in a general metric space, you can treat it as a complete graph, as I said before. And now every subset is connected. Okay, so this is a very simplified version of what we actually use, but the statements are pretty much the same.
But that's original partition. Yair is here to testify. Was strong diameter.
Yeah, I know.
Something else?
No.
Or just the analysis?
Again, sorry?
The original partitions were strong diameter.
Yeah. Okay. No, we use for this simplified version of the result, we use the exact partition, the exact distribution that Bartal used. Okay. Now, to connect this result to the main result, we use a small variation, but it's still the arguments remain more or less the same. So again, I didn't go into the details, but instead of truncated exponential, we use exponential distribution. And okay, so maybe explain what bothers you. So I'm not sure I understand. No, it's okay.
It's okay, I'm not bothered.
So again, the fact is that similar arguments work also there. Okay, so I'm trying to avoid the details, but okay, I'm not sure what you're asking. So maybe ask again, or I'm not sure.
It's okay.
Sorry. What? No.
I think you managed to intimidate him.
Me? I thought it was the other way around. Okay. So, are you sure? I'm not comfortable now. So are you sure it's okay? Really, so I'll talk to you after the talk. No, sorry. Okay. Sorry. No, it's...
Yeah, listen, you were just saying, you were stating two things.
Yeah.
I think you didn't say anything about the relation between them. Or maybe I missed it.
So, no,
I was trying to make you say something about why the partitions are connected to a problem, that's all.
So again, what I showed works in the complete graph, and to make it work in a general graph, you need a little bit to treat some certain subtleties in the arguments. It's not the algorithm works the same, only the arguments in the proof are more subtle.
That's okay.
Okay? Okay. What?
You'll be fine eventually.
I won't. Okay, so future questions. As I said, the only lower bound known is a lower bound of 8, and the upper bound, the best known is polylogarithmic. So we want to perhaps narrow the gap or even close it completely, either for general graphs or for excluded minor families. As I said, for randomized minors, there is a result that applies for excluded minor, which is better than the result for general graphs. Our result it works the same, and for now we don't know anything special about excluded minor graph families. Okay, so I will comment something about that. So we can generalize the problem a little bit, and we can think of if we have a minor closed family, okay? Okay, the term is clear. What's a minor closed family? Okay, so if we have a minor closed family and we have a graph, we want to create a graph G prime that it's not necessarily a minor of G, but it's in the family. So for example, if we have a graph which is planar, we want a planar graph over determinants. It's not necessarily a minor of the original one, but it's a relative. Okay? So this is a slight generalization of the problem, but again, nothing is known so far. Another generalization is perhaps to allow few non-terminals to remain in the graph, and perhaps trade it with a better distortion, which could be better than 8. Okay, 8 is for a graph which is only on the terminals. And again, there is a connection between distances and cuts and flows, but the connection known today is about randomized minors or convex combination of minors, and nothing is known, as far as I know, about a single minor of the graph. So perhaps similar parallel results for cuts or flows are also interesting. Again, there is a trivial, at least for cuts, there is a very trivial claim argument that gives distortion of K. We hope to do better. Okay, so thank you.